Hey, welcome back to another episode of Math Can Be a Hobby. We are working through this beautiful book by Serge Lang, and in fact, today is the first episode in season 2. So get hyped. I have some really beautiful mathematics to share with you all today. In fact, I'd like to share one of the math facts that really inspired this entire channel early last year, way before I even started this series. So, if this is your first time here, hello. Let me introduce myself. My name is John. I am a former mathematics major, former pure mathematics major. Before I worked, and then I worked for 10 years as a software engineer. I worked at big tech companies, including Apple, Lyft, and Google. And nowadays, I'm returning back to mathematics as a second career after tech. I freaking love mathematics, and it's just a dream to be sharing my passion with you all. So I'm a tutor, I'm a YouTuber, and hopefully someday I hope to become a high school math teacher next. Okay, so today I would like to actually set a 30-minute timer and make sure that we try to keep this a little snappier today. So, Intro to Pure Math, Lang, section 1.4. Today we're going to be talking about something very, very familiar, and you might feel like you have nothing to learn today, but that's not true. I can't wait to share something that I bet money that you've never seen. Section 1.4, we're going to spend about half of the session talking through the theory about even and odd integers, and then we will share a beautiful fact related to even and odd integers. All right, so our guiding topics are going to be, first, why is an even plus an odd always odd? Thinking back to elementary school, I don't know, when do you learn this? Like third grade, second grade? At some point you learn this pattern that if you add two even numbers, you always get another even number. If you add two odds, you get an even. If you add an odd and an even, you get an odd. And we can come up with a bunch of examples, but examples aren't a proof. Can we prove that that will always be the case? In order to do that, we need to get more mathematically precise and be able to write down what exactly is an even or odd number. Once we have that tool, then we can prove this familiar fact. After both of those topics, as I said, I would love to share a beautiful fact by Euler, one of the most prolific mathematicians of all time. And as I said earlier, this is in fact one of the inspirations for this channel for me. So I'm excited to share this with you today. Okay, so first, informally, exactly as you remember, even numbers, 0, 2, 4, 6, 8, 10, dot, 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 right? Odd numbers, 1, 3, 5, 7, etc., etc. What else is there to say about that? How I want to challenge you right now, especially if you haven't seen this before. How would you write down what this pattern is? Like this is like to be able to work and in mathematical claims about any numbers, an arbitrary number that's even and a random odd number. We need to be very clear about what that is. So how would you define what an even number is or an odd number? There are multiple good definitions of this, including some that go back thousands of years. So first, informally, one way to define this would be that you can skip count by twos, right? If you just keep adding twos to the number 0, then you get all of the even numbers. Another formulation, you can skip count starting from 1. It's counting by twos starting from the number 1. I think that those are perfectly fine informal definitions. And here's like an image of that. We've got a number line, and the even numbers are skip counting every two numbers. the even numbers are in blue, the odd numbers are in red, right? Okay, so I want to point out we can also extend this backwards and go to the negative numbers as well, skip counting in the other direction. Then you get even and odd, positive and negative numbers. In fact, every single number is either even or odd. This symbol we haven't seen yet, but here's a good chance to share it. The kind of U symbol is a union, meaning all the evens, every number is either an even or an odd. I wrote that here. Every integer is even or odd, also known as this is a partition of the integers. Splitting the integers into two parts. We'll come back to that later. Now, let's talk a little bit more formally. Can we come up with something just a little more formal? Because this will be easier to prove some of the later claims and facts that we need to rely on for more complex mathematical arguments. Okay, so some people in the comment section may have already spotted this one and used this definition the first time. Good for you, if so. An even integer n is one such that n is 2 times another number. So an even number is double some other number, right? An odd number is not a double of another number. An odd integer is one that's a double plus 1, right? So an odd integer can be written as 2k plus 1 for some other integer k. And an even integer is 2 times some number. So 10 is 2 times 5. So k would be 5 for the number 10. All right, so those are really much more modern definitions. I think that these types of definitions and writing even and odd numbers in this kind of algebraic way is something that is only hundreds of years old, not thousands of years old. Like this method of thinking kind of is more thousands of years old, and then this is more hundreds of years old. I mean, the basic idea was always there, even in Euclid, but still. Okay, another note I wanted to give here is, do you remember long division, right? And when you do long division, before you introduce decimals, you work with remainders, like, I don't know, 11 divided by 3. 11 is 9 plus 2. So 11 is 3 times 3 plus 2. It has remainder 2 after dividing by 3. So then dividing by 2 either has remainder 0 or remainder 1. So in that perspective, these two definitions are exactly, the numbers either have remainder 0 or remainder 1. This is just another kind of perspective or definition or way to think about the integers. Another one, let's say, I also like this. If we swap this order, not a lot of textbooks do this, but now in this form, this much more closely matches exactly skip counting by 2s after adding 1, right? If we add 1 and then add a bunch of 2s, that way we get, you add 1 and then you add many 2s or however many 2s. That's another process or way to see this definition. So I kind of wish that books would write 1 plus 2k, kind of, but that's neither here nor there. Let's keep going. So I wanted to pause here and point out that this is the very first time in this entire book. Did I say section 3 or section 4 at the beginning? I did say section 4. I've been saying section 3 sometimes. Okay, so this is the very first time in Lang that he uses the word theorem, which is really cool. So far, he's boxed little mathematical facts or just called them a property of the numbers or something or other. Like in section 2, there's N1, N2, the boxed properties of commutativity and associativity, the definitions of multiplicative identity and other things like that, right? Definition of a negative. But he hasn't yet, and even some of those, there are proofs. He's got like proofs for these boxed, like sum of, here, let me do this. He's got like proofs written. Okay, that didn't work. Whatever, who cares? For the square of a sum formula, for example, there's a proof there. So this isn't the first time that we've seen a proof, but this is the first time that he's used the word theorem. Theorem means something very special and magical to mathematicians. Like all of these are just arbitrary facts. Like all of them are facts, but some of them we consider just more beautiful, more important or something. And for those like really big, important ideas, even sometimes when they're simple, it's not about how complex they are or how difficult they are to prove. It's not like they're like the biggest boss in a video game, like the most difficult boss or something, but they're like the most important key ideas in math. And this one is old. This goes back to Euclid. Like, remember geometry class? Geometry is so boring, dude, but like this fact is also in that famous geometry book by Euclid. And so, yeah, this is the first time that he uses the word theorem, and it does, kind of hold some extra weight. And I've already said it before, the one that we're going to prove is this part. If A is even and B is odd, then A plus B is odd. It's so simple. This is something that we learn when we're young. But I highly doubt that, when you were 5 or whatever, that you learned the proof for this. But you could. Somebody could teach a 5-year-old this. It's not very complicated, actually. Just to see it, there's all the other cases that he writes out in this theorem. But again, we're only going to prove the second case. All right, so as I said, if A is even and B is odd, then A plus B is odd. Well, by definition, now that we have a clear, precise mathematical definition of what even and odd means, we know that A is 2 times some number, right? And B is 2 times some other number. Of course, they don't have to be the same number, m and n, but whatever number they're associated with, A is 2 times something, and B is 2 times something plus 1, because A is even and B is odd, right? Okay, let's keep going. Then A plus B, when we add these, A plus B is 2m plus 2n plus 1, right? Well, we can factor out that too. This is the distributive property from the previous section. Like technically, we could write by distributivity, but at some point, you don't have to write that every single time in your proofs. Don't worry. And well, now this is m plus n is another integer, right? Let's call it k or l or something. I should have used l. Well, m plus n is another integer, so then a plus b is 2 times a number plus 1, right? Simple, dude. So simple. But there's a fully clear mathematical proof, and we get to draw a cute square and everything for it, because now this matches the definition of oddness. So we can precisely state a definition, and then we can do a little bit of algebra and then show like, hey, this new thing that we built matches the definition. So therefore, this number, whatever it is odd. Dude, it's so simple. Like, this is so much simpler than trigonometry, man. Like, trigonometry is so much more abstract to me. Like, graphing, like, a freaking, like, amplitude and, like, phase shift and, like, all of this stuff that or, like, graphing a polar coordinate function or something. Like, we ask high schoolers to do some much more abstract stuff than this, I think. But somehow we feel like it's like proofs are too abstract, like proofs are too difficult. No, I mean, yeah, some of them are very difficult, but some of them are very simple. Like, I think we could be learning this, like, alongside the other stuff. We could take away some of the pre-calc that we do, and we could add some elementary number theory. So this, I hope you enjoyed that. Now, homework for you. Do the other cases. They're all so similar. Like, now that you've seen one, you can prove the other ones for yourself. And then you'll be able to be very confident for the rest of your life that anytime that you add two odd numbers, you get an even number. Like, you know that for a mathematical fact, which is so cool. Now, after that, what else? What are the other properties? Even times... I guess I said an even number times itself is even, and an odd number times itself is odd. In fact, you can do that for even times even, and odd times odd. It doesn't have to be the same number. But yeah, an even times an even is even, and an odd times an odd is odd, and an even times an odd is even. You can prove all of those cases pretty much the exact same way. So then you can also prove kind of the reverse of that previous fact. If a square number is even, then the square root or the square root of that square number is even. So 36 is even, therefore 6 is even. 49 is odd, therefore 7 is odd. 7 must be odd. And reverse, if a square number is odd, then the number is odd. Amazing. So cool, right? All right, now let's move on. Let's see some new, like, really pretty brand new math. I bet that you haven't seen this before. Now for something different. Did I put another? No, I didn't. All right, partitions. First, we're going to begin with recalling partitions, which I believe I introduced in episode 1, season 1, episode 1. If not, then it was season 1, episode 2. So don't worry, you don't have to watch that. It's not that complex. You can learn it right now. There are 11 partitions of 6. So if I have 6 apples, I can keep all 6 of them for myself. I can keep 5 of them and give 1 of them away. I can keep 4 of them, give 2 to one person. I can keep 4, give 1 to one person, 1 to one other person. Like, what are all the ways that you can split up a positive number? Well, there are exactly 11 ways if you don't count reordering. If you consider, like, reordering the same partition, then there are exactly 11, and they're all right here. Okay, so we've seen that before. Now, just like definition of even and odd, mathematics is all about creating new definitions and then trying to prove things with those new definitions. Mathematics is all just an invention, and it's just pretty and fun. Let's create 2 new definitions. First, we're going to have an odd partition. Then I'm going to show you what a distinct partition is. I'm not going to write down the definition immediately. Instead, I want to begin with an example. Now, remember, examples are not proofs. Examples are not yeah, a proof, but we can begin with an example, and this is a puzzle for you. Can you find the mathematical definition, like a precise mathematical definition for an odd and versus distinct partition? I'll tell you that the first one is distinct. The second one is odd and distinct. The third one is distinct. The fifth one is odd. The next one is distinct. The one following that is odd. And then finally, this last one is odd. Okay? So those are all of the options. Cool. So pause the video, try to figure it out if you want to. I'll give another example, a simpler example for 5. All right. There are 7 partitions of 5. Let's see if your pattern matches up what you might have in mind. The first one is odd and it is distinct. The second one is distinct. The third one is distinct. The next one is odd. The next one is neither. The one after that is neither. And then the last one is odd. Okay? All right. Cool. So, did you find the right definition? An odd partition of a number. Not everybody does. Even, like, I've asked some mathematicians recently who didn't know this. Who don't know, like a lot of people don't know this stuff. And there was a mathematician recently who didn't get this right the first time. An odd partition of a number is a partition in which every part is odd, right? So if we look at odd partitions of 5, the first one, the only part is 5. 3 plus 1 plus 1, all 3 parts are odd. And then the last one, 1 plus 1 plus 1 plus 1 plus 1, that one is odd as well. Okay, so that's an odd partition. My iPad's almost out of batteries. A distinct partition is a number, or is a partition in which every part is distinct. If I've taught this to little kids, and not everybody knows what the word distinct means. Unique is another way to say it. Every part is unique, or there's no repeated parts. That would be another way to say the same thing, right? All correct, equally precise mathematical definitions. Okay, so we've got odd partitions and distinct partitions. This is a pattern in math that you'll see again and again. We reuse that word odd partition in different mathematical objects. Like a partition is a very different mathematical object than a single number. So sometimes we want to reuse even the same words that we've used in other places. And if we do, we want to really make sure that some of the same mathematical properties carry over. Otherwise, that word isn't a good name, a good word for some sort of concept. Okay, now, a beautiful fact. There's a joke in math that, I don't know, if you don't feel like looking up your citations, I don't know what to say. Yeah, like it's like, if you can't find a citation for some thing that you think is true, you can just say it's by a theorem by Euler. Euler is just one of the most prolific mathematicians from the 18th century. This fact comes from like about 1750, and it's one of his many contributions to math. He did a lot of work with number theory, whereas a lot of people only know him as the E guy, like kind of like pi, but E. the Euler constant. He did a lot more than that. So in the 1750s, I wonder if anybody noticed this pattern already. The number of odd partitions of a number equals the number of distinct partitions of that same number. I like to just write number odd equals number distinct. So let's go back to our tables. Look at this, dude. Look at this. Okay, I'm geeking out right now. Okay, look at this. On this table, there are 3 odd partitions and 3 distinct partitions. Sometimes they're both, but not always, right? In this one, there are 4 odd and 4 distinct, right? That's a cool pattern. Do it again. Do it for 7. I forget how many, 20, I don't remember how many there are for 7, but these numbers get bigger and bigger. So, but you could try it for 7. It doesn't take that long. And this could be like a check to make sure that you wrote all of the partitions. So that's amazing to me. Dude, this is amazing to me. Because what does the oddness have anything to do with the distinctiveness? Like, why would there be a connection there? That's like very bizarre and still awe-inspiring for me. Still actually a very beautiful, like that's actually a really cool, fascinating fact. Like those seem like completely different ideas. Like that numbers are unique and not repeated versus numbers that where the parts themselves are odd. Like, wait. When I learned this, just like a year and a half ago, I was like, dude, I didn't even see that. Like, I took a number theory class in college, and it was a wonderful, fantastic class, but we didn't get to this section on additive number theory. And this is just like really nice. Like, wait, that's fascinating. That's really interesting. So this is one of these math theorems that inspired me to start this channel and inspired me to start really rebuilding my mathematics, like studying college and graduate level math for myself. So I hope you enjoyed it too. I can't prove it for you all today. We don't have all of the tools that we need. We don't have the theory, but I can give you the idea. I can give you the basic flavor and idea of this proof. So as an example, there are 4 odd and 4 distinct partitions of 6, right? And they're here. What we're going to do is we're going to find a way to match them up, right? Sometimes they're the same. Like in this case, 5 plus 1 is both distinct and odd. But then other times, if you can find a way to link them up, I'll tell you that these are the matchings. 6 matches with 3 plus 3. 6 matches 3 plus 3. 5 plus 1 matches with itself. Where are we? 4 plus 2 matches with 1 plus 1 plus 1 plus 1 plus 1 plus 1. Blah, blah. Where is it? 4 plus 2 matches here, and then the last one matches as well. If we can find a matching up, like pairing up one from this side and one from this side, that is called a bijection. This process of like associating one of this type with one of this type, and everyone has a match, this is called a bijection. And it's very important and pops up, this idea in math all the time. And this pairing up method is just so beautiful and simple. Like once you know it, this is not Euler's original proof, but it is a modernized version. It's a little tricky, but I will tell you that the way that it works is the core idea is that every number can be written as a power of 2 times an odd number. That power of 2 could be 2 to the 0, which is 1, right? But every number is a power of 2 times an odd. So 6 is 2 times 3. 5 plus 1, 5 is 1 times 5. 5 is odd, and 1 is 1 times 1. 4 is 2 squared times 1 plus 2 times 1. 3 is odd. 1 times 3. 2 is 2 times 1. 1 is 1 times 1. And then from here, you convert and say that this 2 is the number of times that you add the number to itself. Like 2 3s added together. And in this next one, 1 5 and 1 1. The next one is 4 1s and 2 1s. And then the last one is 1 3, 2 1s, and 1 1. Like, dude, this is so cool. Like, this is, I haven't gone back and relearned this proof since I learned it a year and a half ago, and I'm like just geeking out about it again. So if it helps, here's another color-coded version of the same table where I try to show the bijection in this example. And yeah, I think that's about where I want to leave it today. This closely relates to the idea of binary numbers and the fact that you can write any number in a unique way to a basis. So this is super similar, very, very related to binary numbers. All right, that's it, y'all. Thank you so much. I really just can't believe the amount of support that we've had on this channel. Thank you so much, for being here, for watching. If anybody is interested in tutoring, I'm a private tutor. I charge the same as an average grad student right now. You could shoot me an email, or if you have any feedback, any suggestions for ways that I can make this channel better, email is the best way, or a comment in the comment section. You can see more videos, or you could share it with a friend or a teacher if you want to. You could help build this really nice, positive community of like-minded mathematics students by joining the Discord. And a couple of people have asked recently, how can I donate to help support what you're doing? And I didn't want to put this here until somebody asked. Thank you. Like, my gosh, thank you. So there's 2 ways: buy me a coffee or channel memberships. I think both of those are really lovely ways if anybody wants to, but never expect it. Thank you so much just for being here. Special thanks to a lot of the people who were here early during my guitar journey and this math journey. Thank you to special thanks. And then thanks to all the channel members, all the hobbyists, including some we've got 3 new people. And thank you to all of the Luna channel members as well. Really freaking appreciate every single one of you. All right. Thank you for watching. Bye. I gotta go. Bye.